So why don't we have a look at the problem on page 130. And why don't you find the axial stress in there, normal stress, axial stress, whatever you want to call it. So what we like to do here is to find sigma. This is page 130. I hope you have a set of the notes now. You know, it's important to have. This is still in the stapled handout if you don't. But so 130, why don't you see if you can find the stress in that bar. Let's start with that. So that's a bar attached to the wall. There's a force applied. You've got the diameter of the bar is 6 centimeters. So let's see if you can find the stress there, okay? I think I'll pause the recording. Okay, so what you're looking at there is the force in the area to get the stress. The area, I think of it as being the area that holds the bar together, that resists the force, that absorbs the force. So that's going to be the cross-sectional area of the bar or the shaft, whatever you want to call it. Okay. And you just divide it in. It's a fairly straightforward calculation, you know. So we're good with that. So just force over area, or P for load, sometimes we call it. So what we're doing there is we're taking the load over the area, like that. So, all right. So something like that. So the area is going to be pi. Now, when you deal with things that are round, shafts and pipes and things like that, usually you call them out by diameter. You want to remember that. You know, that's a common way of calling out things that are round. So you want to take half of that when you do pi r squared. You know, sometimes we just see a number and we just grab it and use it, and that can get us into trouble sometimes. You know, so remember to take half the diameter when you do pi r squared. So that's 0.00283 meters squared. Take the load, which is 80 kilonewtons, so that's 80,000 newtons. Okay. And then divide that by the area. You get 28,294, 212, so that's 28.3 megapascals. So normally what I do on these things is I just use newtons and meters when I'm in the metric system. Then I figure out what unit I'm going to use after I do that. Now, if I remember right, you know, if you can kind of keep track of what units you're dealing with. I think if I remember right, see, normally when you're doing metrics, you measure the load in kilonewtons and the dimensions in millimeters. That's normally how they do it in metric. And I think a kilonewton per millimeter squared, if I remember right, is a gigapascal. I'm not 100% sure on that though, but you know, and so I can't ever remember this stuff. So being as I can't always remember how these units combine in metric, what I do is I just go to the fundamental units, newtons and meters, run it out, and then I look at it and go, okay, that's a meganewton or or a megapascal or a gigapascal or whatever. So that's normally how I handle that. Okay. And I'm not sure if this is what I want or not. Maybe not. Let's see. Yeah. Why don't we just get a quick check on that if I can get there? Probably this one, right? There we go. So, yeah, 1 kilonewton per millimeter squared is a gigapascal. So that's the common units that you use in structural for metric. But as I say, I don't really do that. I can't remember all that stuff. So what I do is I just get everything into the standard units, which are newtons and meters. And once I do that, then I see I got 28,294,000. So that's 28.3 megapascals. Mega means 10 to the 6, which is million. Okay. All right, so that's the stress. And that's one of the main things we look at in this class. Now, the other thing we look at is strain. Now what strain is a delta, which is a lowercase Greek letter d. That's a change. You might know that from mathematics or something. We use the lowercase for what we're talking about here. And then you take the change in length and you divide it by the original length. And what you get out of that is a proportional lengthening. It's the delta, the amount of change in length, divided by the original length. By convention, it's the original length that you use, okay? And so you just take the delta divided by the original length, and that gets you what we call the strain, which is epsilon, okay? It's like a backwards letter 3, or number 3. See what that is? See, delta, of course, is the fourth Greek letter. It turned into our D. That's why the delta looks like a lowercase d. I'm just trying to help you remember this stuff. And then epsilon, of course, looks an awful lot like an E, because that turned into our letter E. Okay. So epsilon, which is the strain, is delta over L. So why don't we have a look at this thing we're dealing with. This is page 150 here that I'm looking at. So the basic formula is epsilon is delta over L. So why don't we apply that to this problem here? So if we want to find the strain, which is epsilon, that equals delta over L. What's delta going to be on this one? If you look at the original dimension of the bar, and then the dimension after you apply the load, what's delta, do you suppose? How much has the length changed? Yeah, not a whole lot, right? So 0.30, 3, okay? And then you divide it by the original length. Now, I keep everything in meters here. That way I'm getting the unitless value that I want for strain, okay? So you take, that's 3 zeros, 0.0003, divide it by the original length, which is 1.2. And when you do that division there, you'll get the strain. That's the amount of lengthening. Now, typically for structural type materials, these deltas are quite small. So strains usually are very small for steel and concrete and wood and things like that. If you get into plastics and stuff, you might have a lot more. We're using more and more synthetic kind of materials all over the place, really. They're putting like a blanket on top of this building here to get those beams to kind of lock together for the seismic upgrade. So, even in civil engineering, we're starting to do things where we use synthetic materials. But the old kind of structural materials, steel, concrete, wood, brass, stuff like that, you're not going to see much delta at all, okay? So there's delta, and there's delta over L, which is 0.00025. Now, when you call out strains, usually because they're so small, they often call them out as a 10 to the minus 6, okay? So that's a very common way to do it, always using 10 to the minus 6 because strains are very small. The metric prefix for that is micro. So a common abbreviation there for the actual answer is 0.00025. A common abbreviation, it would be 250 times 10 to the minus 6. And it's common just to put that micro symbol after the number to mean 10 to the minus 6. That seems to be a common thing to do. Yeah, question there? All right, so that's stress and strain. And so, again, I mentioned on page 250, I have a lot of the information on this, what different things are and the letters that are used. So now we've got sigma for stress, which turned into our lowercase s. It's like a circle with a little horizontal line on the top. We got delta for a change in length, lowercase delta. And then we've got epsilon for strain. Okay, those are things we want to remember. And we want to keep track of all these things. All right. Now, we've talked about stress and strain, and as it turns out, there's a relationship between those two things. They're tied together functionally. And there was some research that was done on this many, many years ago. And so now there's kind of a standard stress-strain test that's done on materials because you want to have some idea if you apply a certain stress, how much strain will you have? Or if you can measure the strain, what kind of stress is that? So the two are related, okay? And what you do to do this test is you take what are called coupons. They're milled pieces of metal. What you see there is titanium on the left, I think it's aluminum in the middle, and then a mild steel on the right. And what you do is you take these samples and you mill them to a good shape. Your goal here is to do two things. One is to get a standard cross-section on the shape so you know the area so you can calculate the stress. The other thing is to get all the cracks and imperfections out of the surface so that you get a nice smooth, even pull when you pull on these things. Because what you do with these is you pull on them, and your intent is to break them. And as you do that, as you go through that process, you measure the elongation. Okay, so here's an aluminum sample that broke. Okay, and then here's the steel. Right there. See that broke across? Okay, so these are test coupons that were failed, okay? And you gather data on them as you fail them. So what you have there is a hydraulic machine that has strong enough to pull these metal samples apart, which requires quite a lot of force. And then also you could put something called an extensometer on there to measure the elongation of them as they fail, okay? And the machine will also measure the amount of force that's applied. So between that, what you're going to do is to generate a stress-strain diagram, okay? So stress on one axis, the y-axis, strain on the other axis, the x-axis. And is this page 120? I don't know what page. 126, thank you, 126. So this is page 126, okay? So why don't we have a look at a couple of these tests, and let's just take a look here at some. I've got some videos in Moodle, so if you're online, why don't you have a look at these three videos? None of them are very long. I can't show them in my recording because of the copyright problems, but they're there. They're embedded in Moodle. You can have a look if you're online. All right, so hopefully you've had a look at those three videos. The one thing I'll point out is that first one, the graph was load versus elongation. The actual graph that's used, at least in this country, is stress and strain. So you do have to remember to convert load into stress and elongation into strain. Okay. So let's have a look here on page 126, I think it is, so at this graph. Now this is an idealized graph. I just kind of sketched it up so that we could look at it and work with it. It's pretty, actual materials will be a bit different than what you're seeing here, but I'm just using this to illustrate what's happening with these materials. Okay, the first part of the graph is a linear portion. You've got stress, which is sigma, on the y-axis, strain, which is epsilon on the x. So sigma is the load over the area. The strain is delta, the elongation over the length. Now what happens is you start at 0, 0. When you start applying load, the material starts to strain, okay? So as you apply load, you apply stress, what happens is the material will elongate. It'll get longer, and that'll cause strain. There's a linear portion of the graph for the first part of the test. Now, if you use an actual sample, that's not going to be perfectly linear, but it's going to be pretty close. And you could pretty much call that a straight line. Okay, so the slope of that line is what's called E, okay? So E is the modulus of elasticity. It's the change in stress divided by the change in strain, which will get you the slope. But being as you're starting at 0, 0, it's also just the stress over the strain, sigma over epsilon, okay? So if you take, if you're on that straight line portion of the graph, and you take sigma and divide it by epsilon, you get what's called E, the modulus of elasticity. And that's a number that we use a lot when we're doing design work, because when we do design work, we stay in this portion of the graph. And we want to know for a given strain what's the stress and vice versa, okay? So that's just like taking a rubber band and pulling on it. You'll get a definite relationship between stress and strain. There's a number, a constant, that will give you that relationship between the two. Now the top of that linear portion of the graph is called the proportional limit. So that's the first number that's kind of designated on the graph, the proportional limit. Okay. Now what happens after you get beyond the linear portion of the graph is you start getting extra elongation for a little bit additional pull. Okay, so that graph will start to get flatter. Okay, eventually you'll hit what's called the yield point. Okay, now what's happening here, if you look at the atoms that make up these materials, is when you're in this portion of the graph, you're stretching out the bonds in the atoms. They're like springs, and you're stretching them out. Once you get beyond what's called the elastic limit, you're actually starting to tear the bonds apart. You're not just stretching them, you're actually breaking some of the bonds. When that happens, the material starts to yield. So you get a lot of extra elongation for a very small extra amount of stress. The material just kind of give up. And what's happening is all those atoms are sliding around is what they're doing. Okay? And this isn't the same thing, but it kind of feels the same way. If you ever blow up a balloon, you know how it's kind of hard at first, and all of a sudden it'll just expand rapidly? That's kind of what I think about with yield. The material just kind of gives up, and everything just starts sliding around, and it really starts to deform. Now, what happens here, if you look at a metal, which is usually what we're dealing with here, it actually is in a crystalline structure. It's not a perfect crystal like a diamond or a ruby or something like that, but it's still in a crystalline structure, but it has these lines, these fault lines running through it of imperfections. What happens here when you really start to yield the material is all these fault lines start sliding together and they run into each other. And that hardens the material up a second time, and that's called strain hardening. So when all those fracture lines start to intersect and interfere, they harden up the material a bit. So you get a second rising section of the graph. And that will continue until you get failure. Okay. And the failure stress is called the ultimate stress. Yeah, question?
Is the material significantly weakened when it's in that strain hardening area?
Is it? I think, is it weakened? I guess these terms that we use kind of in a conversational way take on a much more technical meaning when we start talking about this stuff. It is actually.
Is there a purpose for that in the industry where they would intentionally bring it to that point?
You can, and then back it off, and you kind of what you've done. Well, there's all sorts of things you can do in material science, and people discovered this stuff long before they had the graphs and all that. One of the real examples of it is, you can do heat treatment, you can do strain hardening. There's all these things that you can look at. If you look at like sword manufacture back in the day, they wanted the core of the sword to be ductile and flexible. They wanted the edge of the sword to be strong and brittle to hold an edge. And so, they did things with annealing, and they did different material properties that kind of learned by trial and error. So right in here, normally there's a trade-off between ductility and softness, so how much it'll stretch and how soft it is, and hardness and brittleness. So a hard material is often quite brittle too. So you can do different things to kind of play around with the materials. So I'm still not quite sure what to do with your word weaker there.
That was a pretty loose term.
I know, I kind of know what you mean by it, but I'm kind of struggling to come up with a nice, clean answer to what you're asking.
Saying that it was more brittle, kind of answered it
it
would be easier at that point, like you struck it to
I would think it would, yeah, because you kind of there's no give in it anymore, so to speak. Okay, and a good example of that would be like cast iron, which is a very brittle material, quite hard but brittle. You could hit a cast iron stove with a hammer and it'll break, versus a ductile, softer steel, which is more ductile and more able to give. Yeah.
So if this represented just like a piece of the truss and a bridge, over time, could you use this to determine how much time it's going to take for it to fail?
That's another test, and that's repetitively loaded. That's cyclical loading. And you can get cracks and things that form in a material if it's been strained and then the strain's released over and over again. You're basically strain hardening the material is what you do when you do that.
But could we analyze it in a way to say, in this many years, it's going to be at this point in graphs, we need to replace it?
Yes, yeah, they do. And the way they mimic that, they can try and mimic it. What they do, they put it on a machine that just repetitively strains it, then releases, strain, release, and what they're counting is the cycles of strain and release until it starts to fail. Same sort of thing here, but a different test and done differently. And material science is really interesting stuff. It's half, it's half science and half black magic kind of stuff, especially with metals. I don't really know it that thoroughly, but it's really pretty interesting. So that would be a cyclical load test. And what they do, that's typically done in manufacturing companies, and they kind of build a normal curve for their samples. And of course, they're very conservative with how they rate their materials, with how long it can age, because of course failure is always a very bad thing. So, and there's some little bit on that too, where they kind of how they rate it based on all the samples they take. Okay, now one thing that's happening here, if you look at this graph, is you see this strain hardening starts to go up, and then it tails off at the end. The reason for that is the necking. See, if you want the actual stress, which I'll put in a dashed red line here, that will always increase until failure occurs. But the problem there is finding the stress depends on the cross-sectional area. And it's hard to track the true cross-sectional area of the sample when it starts to neck. Okay? So the convention is to use the original cross-sectional area throughout the calculation, and to use what we call the nominal stress, which is based always on the original cross-sectional area, even though that changes when the material starts to neck. So you use the nominal stress typically, and you get that drop-off at the end. Because even though the actual stress is increasing, you always use the original cross-sectional area for that calculation. Okay? So it does appear to drop off at the end. Okay. Now that's kind of an idealized graph. And I've got those definitions down below there on page 126. Now another couple aspects of this graph is there's something called the elastic limit too. As long as you stay below the elastic limit, you haven't really destroyed any of the chemical bonds. You're just stretching them and unstretching them like springs. So if you go up to that elastic limit and then unload, it'll come back to its original location, to the original length. That's beyond the proportional limit, just slightly, okay? But once you go beyond the elastic limit and unload, it won't return to its original length. It'll have what's called a permanent set in it, where the original length will be slightly elongated from the original length, okay? So what you have there in that portion of the graph are 3 points that are all kind of close together. The proportional limit is the end of the straight line portion of the graph. The elastic limit is the limit which, once you reach it, if you go beyond it, you will no longer rebound to the original length. You won't return to the original length. And then the yield point is the point where this yielding phenomena starts to occur, where the graph really flattens out. And for a small change in load, you get quite a bit of elongation. Okay, so those are the 3 points in there. All right, let's see, we got permanent set there. Now, the last thing on these graphs is the yield point in a real piece of data can be hard to find, especially when you have more ductile materials like plastic or a soft metal that will elongate quite a bit. So there's a standard way to find a yield point that is created especially for these more ductile materials, but it's used pretty commonly across the industry. The idea here is to create a yield point that everyone will find in the same way. So instead of people looking at a graph and going, yeah, I think the yield point is right about here, this is more of a standardized way to find the yield point. And the way you do it is you start at a strain of 0.002, which if you consider this to be on a percentage basis would be 0.2%. That's just a value of strain that you would start at. Then what you do is you draw in a line that is parallel to the linear portion of your graph. And wherever that intersects your graph, once it starts to turn and flatten out, by definition is the yield point. Okay? So that's the standard way to find a yield point. So are we all right with that? And I'm going to give you some homework, and that's how I want you to do it, okay? That way everyone's getting the same answer, and that's why this is used, to standardize it. So instead of someone just picking a point out of a graph, everyone is doing it in the same systematic standard way. Okay? So we doing all right with that? Good, okay. So that's just a little bit on material testing. And you can take a whole material science class. I think the civils do, but it's confined to civil materials. So, it's structural stuff, and also, I don't know if they put soils into that or not. Probably not. They probably do soils separately. And then the mechanicals, I think you take a materials class too. It's really interesting stuff, and it's not quite so equation based. Sometimes is what we're used to. It does have a lot of stuff about chemistry in it, which makes it pretty interesting stuff. Now, the other thing I just want to touch on here is let's find E for this material now, okay? Because if we're back on page 130, if we have a graph like that, we could find E by finding the slope of this line. So we got stress, we got strain. Strain is epsilon, not to be confused with E. They're different things. Okay, now what E is the slope of that straight portion of the line. So it's the stress over the strain. E gets you that property of the material that tells you how much it elongates for a given amount of load. Okay, so if we just take, for this example, what we have here, you calculated a stress and you've got a strain. So if you just take those numbers and divide them out, you'll get E, which is the slope of that linear portion of the graph. All right, so if you just divide those out, you'll get E. So 28 times 0.3 times 10 to the 6 divided by 0.00025. The 0.00025 is just a proportion. It's a unitless quantity. So E comes out to be in pascals, newtons per meter squared. In this case, it's about 113. So that's the slope of the rising limb of that graph, which is the linear portion of the graph. That's the part of the graph we do our design work on. So it's very common to use E to do kind of a transformation or converting stress into strain and strain back to stress, if that's what we need to do. We use this value a lot. And one thing I want to mention is, remember the difference between E and epsilon. Epsilon is the Greek letter, that means strain. E is the English letter, and that is the ratio of stress to strain in the linear portion of the graph. Okay. And as I said, I have this stuff kind of lined out on page 120. I'd encourage you to kind of, just review that every evening. Just be sure you know what these things are. We're going to deal with a lot of fairly straightforward relationships, but there's quite a few of them. So we have to keep track of all these different relationships and what they mean. Okay. Right. Another thing that we deal with here is just structural materials. All right. Typically, we work a lot with steel when we're doing structural work. That's very common. It's made of iron and some other trace elements, notably carbon, and that's a very common material that we build things out of. Now, steel makes kind of I think it's a cubic sort of lattice to it. It has a cubic structure for the iron molecules. They go into that type of structure. And what happens then is you have the gaps in the cube, okay? And I think it's cubic. Don't quote me on this. I don't do a whole lot of material science. But if you look at this, you get the carbon, which I probably don't want to be red. Maybe I'll make that black. They get into a cubic sort of shape, a crystalline shape. Not a perfect crystal, quite like a like a diamond or something, but something like that, okay? So that's the shape of the carbon. Now what happens, excuse me, not the carbon, the iron, I'm sorry, I misspoke. That's the iron. This chemical symbol for that is Fe, right? Now what happens when you make steel is you put carbon in there. And the carbon, and I was saying iron originally, or carbon originally, I meant iron. So the iron is what makes up most of steel, and it creates a pattern like that. Now in the middle are where the carbon atoms go. And what they do is they stiffen up the iron. Pure iron itself is kind of soft and malleable. Okay, it's not as strong as you would think. When you start putting carbon atoms in the middle, though, you stiffen it up. Okay. Now, the one primary way of controlling the properties of steel is to control how much carbon you put in there. Okay. Now, a lot of carbon stiffens that up considerably, and you end up with something like a cast iron, which does not deform much at all, and is very holds an edge. It's quite brittle and hard. Okay. Less carbon gets you more of a ductile steel that is softer, maybe not quite as strong, but more ductile. It bends more. It gives more. Okay. So when you're making a structural steel, which type do you suppose you'd want to go with? Ductile and brittle. Yeah, I think what you do, you use a softer steel that isn't quite as strong, but it's ductile, and it's called ductile iron. And there's reasons for that. The first thing is, if you have a failure on a structure, you don't want to have a brittle fracturing failure like glass, like cast iron would fail, because it's sudden. You get no warning about it. There's no elongation, and it just shatters. You do not want that. What you want is more of a ductile failure, where things stretch. You have some appearance of failure before it occurs, so you get some warning it's going to occur. And also, by stretching, it absorbs energy too. So, yeah, right. They need to have that ductility, yeah. Especially tall buildings can sway in the wind and all that sort of thing. So, yeah, you want ductile steel. That's what we use for structures typically, for a number of reasons. Okay, now let's have a look at problem 111. I'd like you to use either MATLAB or a spreadsheet on this one. And what I've done, I've given you some data. And I want you to work with it and to build a stress-strain curve out of it. So you can use either Scilab, MATLAB, and I would encourage you to get used to that if you're a mechanical type engineer, because you use that a lot in the junior year. The civil and construction types generally use Excel. But the mechanical types, they often give you assignments in Scilab and MATLAB. Okay, and what I've done, I've given you some data there. It's problem 112, which is in the front of the packet, the second or third page in of the front of the packet. And maybe it is 111, right? 111? Yeah. Okay, it's not 112, it's 111. Okay, and what I do, I just give you some data. And so what you're going to do with that is you're going to just take the load data, convert that into stress, and then take the deformation data and convert that into strain, and then plot it up. Now, a few things on this. Be sure you do those conversions. So convert the load into stress and the elongation into strain. If you use Excel, you've got to use a scatter plot to plot the data. Don't use an XY graph. Excel is based on business functions, and if you use an XY graph, it spaces each piece of X data an equal distance from the previous one, and it'll skew your graph. We want to use a scatter plot. That's important. Okay, now I do want the answers. I ask you specific things. I think I ask you 4 things. Define E, the yield stress, the ultimate stress. Is there one other thing I asked? So E, the modulus of elasticity thing. The proportional limit, the yield stress, and the ultimate stress thing. So please give me those numbers, okay? And don't just turn in a graph. Give me those answers boxed in. You may not get my exact answers, and that's fine. We're reading a graph. There aren't exact answers. But keep in mind that, when you're working as an engineer, the client doesn't just want a graph. The client wants answers. That's why they hire you. So get me the answers in a box. Now, I would like you to find the yield stress using that 0.2% offset method. So you can draw that line in by hand if you like, okay? You don't need to do that in Excel. You can, or MATLAB. You can put it in there if you care to, but you don't have to. All right, you can also list your answers by hand. So why don't we just take a quick look at that. Let's see.
We're gonna bring that to the class with us tomorrow.
Oh, no, I'm sorry. This will be due next week. And also, all I need is a printout. Yeah, I don't need the actual file, just a printout. And if you're online, you can just print out your graph and your answers and just turn it in. That'll be fine. Let's see here. If we can get there. There we go. There we go. So there's the problem there. So you're given the diameter of the sample so you can find the area. You're given the original gauge length of the sample. It's 5.08 centimeters. Okay, so you've got load. Let's see. So load is the area. I'd probably just put in a column for, oh, maybe I'll put it over here. Stress is load over area. So I'd use this and I would find the area. And then another column would get you strain, which is delta over L. Deformation is delta. Here's L. Okay? So you're going to get something like that, okay? And so just build the columns like that, enter the data, and then find the sigma and find epsilon. Then when you do the plot will be sigma on the y-axis, epsilon on the x. Use a scatter plot if you're using Excel. Don't use an XY plot. Use a scatter plot. And your graph ought to look something like that. That's what Excel looked like in about 1990, I think. I think they've improved a little bit since then. And you can draw in that 0.02% line. You can put that in by hand, find that intersection for the yield stress, and give me those 4 values in a box. Remember to get those values written down. Now, I suppose we need to know when this is due. What is today's Wednesday, right? Why don't we make this due on Tuesday, okay? So Tuesday, which I think is the 14th. Okay. So this is problem 111. Let's do Tuesday the 14th, okay? So now, remember, we have that stuff due Friday, 102 and 103, is that right? Yeah. Okay, and we'll cover those tomorrow if you have questions, okay? And then we'll cover this stuff on Monday, probably, is what we'll do. All right, so we good? Questions, all right?